Hello everyone, I'm Dario, Senior Developer Evangelist at HTC VIVE Studios, and I'm here to show you how to get started with the VIVE Hand Tracking SDK, which we released a year ago now. I'll be showing you where we are now and what our roadmap will be in the near future. 5 years ago, while showing demos of our original generation of VIVE, actually it was the VIVE Pre at the time, many of the users new to VR were so immersed that they achieved a level of presence that made some of them hold both controllers in one hand and take the other bare hand and reach out into the virtual world and try to interact with it. There was this natural inclination to use their own hands to participate in this new magical experience. Well, we now can provide that option with hand tracking. The use cases differ and in some ways can go beyond what a controller-based input can do, and in some cases it could do less. But hand tracking will not necessarily replace controllers. It will open up new experiences. Our VIVE hand tracking engine will track both hands simultaneously and will currently recognize up to 6 specific gestures, with the latest addition being the victory sign. But of course, we will continue to look into adding more gestures in the future. Our VIVE hand tracking solution, like many others, is a deep learning solution and can provide the following modes. Hand positions, available in both 2D and 3D point modes, and a skeleton mode, which is essentially finger-level 3D positional tracking, consisting of tracking 21 points for each hand. That's 4 per finger and 1 for the palm. The 21-point skeleton can subsequently be mapped to custom hand models, of which we provide some example models. Here's a basic use case for hand gesture recognition. The sample demo illustrates several things, including interactions directly with objects and remote interactions, such as remote grabbing with the user with the use of single and multi-hand gestures. The sample shown here is included in the SDK with full source code. As you can see here, he used both hands to select an object and then a different gesture to actually lift it up and throw it. In case you may have not heard, in some use cases we can even support the original VIVE, as well as even some Android phones. This chart shows you which modes are supported per platform. As you can see, the original generation of VIVE only had one camera. It doesn't support 3D positioning that's available with stereo cameras. And here are some performance specs based on frames per second measurements. On this slide, we have PC-based VIVE options. And as you can see, like I just said, the original VIVE didn't have stereoscopic cameras, so it can't really do the 3-point mode. In this next slide, we have the Android-based devices, including our standalone. You can see that without the stereoscopic cameras, again, on the Android phones, you have the limitations there as well. And of course, all these performance specs are subject to change as we continue to improve performance. So here's what you get when you download our SDK. This is the zipped up package here shown. It contains several folders, support for Android, Unreal and native C, C++, as well as the full online documentation and the latest Unity package. As you can see in the current latest release notes, and this was just released this past month, we are continually improving the tracking experience. We're reworking the algorithms to reduce jitter, and we're adding a new model. In this case, we introduced a robot hand. Using the SDK, well, as you can see here, we have quite a number of support for a number of engines. We have low-level support for C, C++, and that's basically the foundation of the other implementations, of course. Here's a look at the basic functions for starting, stopping, and getting gestures. We'll look at the C API first, as that's the building block for the others. Note how you need to specify the backend mode consisting of either auto, CPU, or GPU. Normally, you just set it at auto, not worry about it, but we give you those options for specific use cases. Equally, there's the other mode, that's the other enum, gesture mode. And as we mentioned earlier, there are three main modes, which is capturing 2D points, 3D points, and the skeleton consisting of the 21 points. And here's the corresponding stop gesture detection method. Unlike the other one, it's a blocking call, so it's just something to keep in mind when calling stop. And here's how to obtain the gesture data. This struct and enum represents all you need to know about the gesture being recognized and the position points. Moving now to how it's done in both Unity and Unreal. Here we see the start and stop capabilities that's available in the gesture provider script in Unity. So that'll get called in on enable, on disable, on application pause, and so forth. On the Unreal side, you'll basically be adding a Vive hand tracking component to your scene, and you'll have the ability to do the start and stop detections with the similar options, of course, choosing which mode you want. Since startup is not immediate, or while you process permissions for the camera, or while you wait for the deep learning pipeline to set up, so it's useful to check on the status with this API, as the engine may still be starting, and to check for any errors. Okay, now here's how to get the left and right hand results directly. Just call left hand or right hand, and they both return a gesture result, as we've seen before. It's very similar, of course, in Unreal as well. You can also check to see if there's been an update in the current frame, and this is to avoid any additional processing if there hasn't been an update since the last frame. Here's another basic use case. This is for drawing or potentially sculpting with your hands without using controllers. Again, gestures help toggle between different drawing or erasing modes and so forth. In this case, you can see him toggling between different modes, whether to interact with the planets or whether to continue drawing. And it's a combination of gestures with both hands. And now I can actually use the 6 DOF capabilities of walking around his artwork. Here's another use case. This is an actual application available now on Viveport, illustrating the 2D or 3D point modes. So this is without actually having to show the hand. You can actually have interactions, basic, turn the page interactions, calling up menus, being able to use, in this specific case, it's also using the pass-through to recognize the QR codes in order to show different content. But essentially, your gestures here are basic point-based gestures in 3D or 2D. So technically, if it's 2D, you can actually use this in the original Vive. Okay, so here we're going to customize. I'll show you how to customize the hand model. And this first, I'm going to talk about what developers need to do. Once they have a model, they import the model as an FBX file into your scene. And then you add a model renderer script that we provide so that you can add to your hand objects. And that's where you're going to set all the joints and make sure it actually takes that rigged model and is able to move it. We provide a robot prefab for this latest release, and we also have a hand prefab from our previous release. So you have at least 2 models as a reference. The skeletal mode mapped to the hand models will be more intriguing and immersive, so that you can easily import existing build or build custom models to import into your game engine. In Unity, we provide a model renderer script, which will take care of mapping the rigged model to the gesture results position values that will move your actual hand joints. Shown here is a mirror mode that copies the 21 points of your left and right hand tracking results to another pair of virtual hand models, giving the illusion of two pairs of hands when only one pair is being tracked. Artists and developers have the following set of guidelines for creating a skin mesh rigged model made of the 21 joints. I'm not going to actually read this list, but you can see that there's some specifics to rotation and axes of the fingers, and especially the default state of the hands, with the fingers open, and just some prerequisites that you need before exporting it into your game engine. I've personally found that some of these 3D tools may require some more specific tweaking when exporting in FBX, especially for the use in Unity. For example, in one case, I had to make sure it had animations. So we can include animations, just make sure that it's at a state where you can create a skin mesh renderer when you import it into Unity. So let's start from scratch in Unity and just go through this step by step. As previously mentioned, simply add the gesture provider, which is a C# script component, onto your main camera. Now that main camera could be inside a VR rig. Just find your main camera for your VR scene and simply add this script. And as you can see, the options here in the inspector is which backend you want to, processor backend you want to handle the hand tracking. It could be CPU or GPU or auto. I recommend auto. And of course the mode. As we mentioned, there's 3 modes: 2D, 3D, and skeleton. We're going to go with skeleton. Next, make sure the nodes match the corresponding joints of your rig, and also notice you may specify the mesh to use from the FBX file right above that list. And at the very bottom, also notice that the collider type is specified. This will allow this script to create the colliders for you. And lastly, step number 3, this is where you handle or manage the specific gesture recognition and the corresponding event actions to take place based on that recognition. Note that it can handle 2 state conditions: prepare condition and trigger condition. These are more like 2 steps for the same action. Let's say, for example, aiming and then shooting, or aiming and then grabbing, like we saw earlier. And optionally, there's also a reset condition to determine what happens if you lose tracking. Now here's another view of the sample project. Here in this case, we can see how to use a gesture to toggle between the models. But what I really want to demonstrate here primarily is showing interactions using the model's colliders, as well as how to pick up an object using a collision trigger event, while also using a gesture to indicate the grabbing intent. And in this case, we're using the OK gesture to initiate a grabbing mechanism. Now, when grabbing in VR, you're probably aware of how similar this is implemented when using controllers. Here we're illustrating what it means to rely on just colliders versus colliders and gestures. To illustrate this further, I can show you how difficult it can be to pick up a tiny cube with the colliders alone. This is why you should think these things through and the options you have for grabbing and hand tracking. Try combining existing solutions or come up with new ones to make it seamless and not just realistic by relying on just colliders alone. Now earlier we saw that we can grab things remotely. Here's how you can use a gesture, in this case, the natural point gesture, to turn on a laser pointer on your finger to remotely select a menu items using standard Unity UI that normally you would use raycasting with controllers. Simply repurpose your raycaster to emit from your finger instead of the controller. In fact, you should be able to reuse most of the same code that you were using controllers and I suggest always supporting both, ideally with the same tool. Note how natural it is to use a poke gesture to indicate a button click, much like the collider way of pressing a button. Okay, here's some tips we've been discussing so far and some additional ones I've learned while implementing hand tracking. Don't assume 100% accuracy to avoid additional work to make it realistic. What I'm saying is don't expect ideal lighting conditions. As we saw earlier, leaving it all up to finger colliders isn't going to always work. So do add animations and or customize colliders. Use gesture recognition to trigger state changes for both. In fact, you may even consider animating colliders for those special use cases that require better grabbing or holding onto mechanics. So either one or the other or both combined or some new approach you can take. Do use natural interactions. Try falling back to position-based gestures like sometimes we've done in the past with controllers. Again, this would include things like pokes, swipes, some universal gesturing type of motions, circular motions, sign language, etc., etc. Do reuse your controller code for interactions as much as possible, and you can do this by abstracting as much as possible from toolkits, or just rewrapping those toolkits so that you can actually fall back and go in both directions. In some of these experiments, for example, I've reused the VIVE input utility, VIU toolkit, our cross-platform VR toolkit for all your controller and tracker needs, can be reused for hand tracking as well. Another way of implemented controllers dropping out to hands is by shrinking the raycasted UI, for example, if you have a row of buttons, to something that can be small enough to rest in your hand or to have a pull-out equivalence menu that comes out of your hand, so that you can use basic finger colliders to push buttons. So there's several approaches to doing raycasting or a mix of raycasting and colliders. Consider falling back from controllers to hand tracking for all menu-based user interfaces. Include both near and far interactions, collider-based or ray-based, much like we're seeing with eye tracking falling back to gaze, or with audio falling back to requiring subtitle options. Always have a fallback in either direction. Basically, it could be due to bad lighting in one direction or due to dying batteries in the other direction. And lastly, please play with scale and position. Make it magical. Surprise with the unexpected. Follow what other hand tracking developers and creators are doing. For example, that mirror effect that I showed you earlier in one of my experiments was inspired by Denise Kunert from Switzerland, whose video on Twitter fooled a number of viewers. His implementation, of course, was much cleaner and had much more realistic collisions between the hands. Here's what's coming up in short-term roadmap. We will be having, of course, UX improvements. We'll be adding a new gesture pinch support, initially just with thumb and index finger only. Again, it's not necessary to support all the combinations. The more natural ones make more sense. So, for instance, when you reach out to grab something or to resize something, that thumb and index fingers gesture is really more common. Custom gesture support, that's coming soon. The Cosmos XR faceplate support. Well, the higher resolution of the XR faceplates is going to bring higher fidelity, so that's coming soon as well. And Valve Index support. We already work under OpenVR, so it's not that far-fetched, other than, of course, supporting a different camera characteristics, and some deep learning that will be required. So, to end, please give it a try and give us your feedback. Here are the direct links, but you should be able to easily navigate from the developer.vive.com site. Please do check our forum because we have our engineers available there to answer all of your questions. In addition to the above resources, for those interested, I'll be posting additional sample code that you've seen here on GitHub. The GitHub, you can just simply search for VIVE or VIVE software.